Hello friends, welcome to MOL-MENTUM. What is the difference between the humans and the plants? Why do we need to breathe while they just need that sunlight? So biology tells us that we are different, but chemistry tells us that we are almost exactly the same. Take a look at these two molecules. So look at the difference. So just look at this metal ion, magnesium on chlorophyll and iron in this case. Ignore this outer edges, this porphyrin ring for a second. What is one major difference that we see in hemoglobin and chlorophyll? So in hemoglobin, we have iron as the central metal, whereas in chlorophyll, we have magnesium as the central atom. Exactly. That is the single swap of metal ion changes everything. So today we are starting the coordination compounds. In this chapter, that central metal like iron or magnesium is our VIP. So the large ring around it. So this ring around it is called a ligand. So we are going to learn how these ligand attach to the central atom metal, create a molecule powerful enough to carry oxygen in our veins or capture solar light from the sun. So this is all about coordination chemistry of class 12th. So coordination chemistry, as we all know, it arises because of the coordinate bond. So what is a coordinate bond? Whenever any electron rich species, we will name it as ligand in this chapter. So having a lone pair of electron. So when a pair of electron is donated to some metal ion. So that particular type of bond is called coordinate bond. And so the entire chemistry that of coordination compound revolves around this coordinate bond. Look at these two molecules. So although we will discuss this isomer at the end of the chapter, but look at these two molecules. What is the difference? This part, this part is same. This part is same in both the molecules. So what is the difference? The difference is in this part. So in this case, you can see that blue ball is connected to this metal. Whereas in this case, blue ball is not directly bonded to the atom, whereas red ball is connected to the this central metal. So that makes the entire difference. So these types of compounds in which everything is same, just the atom which is attached to the central atom is different. So this type of isomerism is called um, linkage isomerism. So this we will discuss. So you can see just by with the change of one atom, the color and the entire properties of these two compounds are changing. So this is the foundation of coordination chemistry. So as we all know that coordination compounds are some sort of a salt. So as we have studied in class 10th, that a salt is formed by the neutralization reaction of acid and base. So we have studied the simple salts, like when acid base react, they form salt and water. So these types of salts are of two types, the simple one and molecular, or what we call as addition compound, in which one or two salts gets, they come together. So this is the example of simple salt where we have potassium hydroxide and HCl. These two combine to form a simple salt, potassium chloride. So when this potassium chloride is dissolved in water, so it decomposes or it dissociates into K plus and Cl minus. So these salts are a strong electrolyte. They gets ionized in water. Similarly, we have another example of double salt. So let us cover the double salt first. So the difference between this double salt and this coordination compound is a double salt is a combination of two salt, like we have potash, alum, what we call as fitkiri, or we have mohr salt, mohr salt. So this is also a part of our titration part in qualitative analysis. We have titration also. So a double salt is a compound prepared by combination of two salts. So where two salts get they come together and form one addition compound. So like in case of the Mohr salt is the common name, and the chemical name is ferrous ammonium sulfate. Ammonium sulfate. So and the formula becomes ferrous sulfate dot ammonium sulfate dot 6s2. So we can write the formula of Mohr salt, ferrous sulfate FeSO4. So FeSO4 whole twice dot ammonium sulfate. So we have NH4 whole twice, then SO4, and then 6s2. So this is Mohr salt. And the second type of example we have carnallite, and the third one is potash alum, what we call as Fitcari. So this is the formula of potash alum. So in double salt, they completely dissociate into its ions. So when they are dissolved in water, they give their simple ions when they are dissolved in water. So it can be easily analyzed by determining the ions present in the aqueous solution. Now, how these addition salts, or the common name is a double salt, these are different from this coordination compound. Is coordination compound, it does not dissociate. So a complex salt is it is a coordination compound is a type of complex salt in which central atom having coordination bond with the ligand. So it forms a coordinate bond where there is a transfer of the pair of electron, and this too also the coordinate bond is always directional. So direction directional means the movement of electron is from ligand to metal. So the donor to the acceptor. Then this is the most important part of coordination compound, that they do not dissociate into their ions. So they do not give their simple ions. There are a lot of examples we will discuss. The first one is potassium ferrocyanide, K4FeCN6. So this is an example of coordination compound. So look at the difference. We have simple salts. So when simple salts, they are formed by neutralization of acid and base. Double salts, they are the evaporation of two or more salts in stoichiometric proportions. So what is a coordinate salt? So or a coordination compound? It is a combination of Lewis acid and Lewis base. So what are Lewis acids? Lewis acids are electron pair acceptor, whereas Lewis bases are electron pair donor. So that is the difference. So central metal is Lewis acid, and ligands which donate electron are Lewis bases. Simple salts, they ionize completely, whereas these double salts, they dissociate into their constituent and they loses their identity. We have Mohr salt, carnallite, potassium. Whereas coordination compound, they do not dissociate completely, and the complex ion retains its unique identity. That is the important part. So these are the examples, these three. So simple salt, then we have double salt, then this one is the coordination compound. Double salt I have already discussed, this potash alum, Mohr salt, and basically they are formed by the combination of two salts. So either you can write ferrous sulfate, ammonium sulfate. So ferrous ammonium sulfate is the chemical name. Next is basic. We are right now dealing with the basic definitions. So coordination compound or a coordination complex is formed when Lewis acid and Lewis acid and Lewis base they combine, or when there is a transfer of electron from Lewis base to Lewis acid. So the molecular compound, it does not dissociate into its ion. So like we have FeCN whole twice and 4KCN. So when it combines, we get this K4FeCN6, and this is the structure of that particular compound. So we will discuss it one by one. So this square bracket is called the coordination sphere. Then again when this K4 FeCN6, when it is dissolved in water, so anything which is present outside this bracket is going to dissolve or it's going to ionize. But whatever is present inside this bracket is not going to dissociate. So what we will get is only 4K plus as the ion present in this particular coordination compound. This part is not going to dissociate. So that is why, that's how it is different from the normal double salt or simple salts. Okay, then these are the basic definitions. So the ion, or the, it is mostly it is cation. So the cation which is written before that square part is called counter ion, simple ion or counter ion. This is your central metal. So whatever is written inside that square bracket, that metal is called central metal. This is also Lewis acid. Ligands, whatever these, it can be one, it can be more than one, it can be two or three or more different types of ligands are possible in a single coordination compound. So these are ligands, Lewis bases. Then whatever number is written along with that ligand is called the coordination number. And this entire part means whatever is present inside this bracket is called coordination complex or the complex ion. So now suppose if K4 FeCN6 is it dissociating, so what we will get 4K plus. So since the total charge, cationic charge is 4K plus, so this compound complex will have 4 minus, because these compounds are electrically neutral. So we have various types of compounds. So this CONS36, this is also one type of coordination compound in which central metal cobalt is having 6 ammonia ligands. So now there are various applications of coordination compound, like we have discussed the hemoglobin, this chlorophyll, and a lot of examples are there. So coordination compounds are used in the extraction of metals from the ores, like we have silver and golds are they are extracted in form of their cyanides. So nickels are obtained in form of their carbonyls. EDTA is a very good chelating ligand for to remove heavy metal poisoning. So to remove the hardness of water, EDTA is used. EDTA is used. The name of EDTA is ethylene diamine. It could be triacetate, so it will be 3 minus. If it is EDTA 4 minus, then it will be ethylene diamine tetraacetate. So we will discuss these ligands in detail in the coming slides. In chemical analysis, we have various metal ions are used for the detection. So like for blue, red, so Ni2 plus, nickel 2 plus, and palladium 2 plus, they form insoluble color precipitates with dimethyl DMG, dimethyl glyoxime. So they are used for the various types of qualitative analysis, like we have salt analysis. So they are also used as commercial coloring agent. So this what I was talking about, to remove the hardness of water, EDTA is used, ethylene diamine tetraacetate or triacetate. This we have already discussed. So to purify or to extract silver and gold, so they are extracted from their ore in form of their cyanide complexes. This we have started this class with. Chlorophyll is a compound in which this ring, entire ring, this is called porphyrin. Porphyrin. So this entire porphyrin is bonded with magnesium metal. So this magnesium metal is the central metal, whereas in case of hemoglobin, we have iron as the central metal, which is called heme protein, red protein. So hemoglobin is a type of coordination compound of iron. Similarly, chlorophyll is a coordination compound of this magnesium. Then we all are using polythene. polythene. So polythene is prepared using ethene and Ziegler-Natta catalyst. So Ziegler-Natta catalyst is one of the very important organometallic catalyst, which is also an example of coordination compound. So this is the triethyl aluminum and titanium tetrachloride. When it reacts together, so we get a Ziegler-Natta catalyst. This is the structure of Ziegler-Natta catalyst. So this catalyst is used for the preparation of polythene, which is an example of coordination compound. So there are various and numerous applications of coordination compound in our day-to-day life. Similarly, for the detection of cupric ion Cu2 plus. So when we add ammonia, so we have CuH2O whole 6. So when in this solution, light blue solution, when we add a small amount of ammonia, so there is a, the color changes from sky blue to navy blue, dark blue when we add excess of ammonia. So this reaction also confirms that presence of cupric ion, Cu2 plus ion, which is an example of ligand exchange reaction. So it is used for qualitative analysis extensively. So this is a very famous statement of Albert Cotton. He says that probably the greatest conceptual contribution to organic chemistry. So he compared this Werner's theory, comparable in both direct and indirect impact, to the concept of tetrahedral carbon atom in organic chemistry is Alfred Werner's concept of coordination compound. So Albert Cotton says the contribution of Alfred Werner is so huge that it is just like that, the concept of tetrahedral carbon in organic chemistry. So tetrahedral carbon is, foundation, is the beginning of organic chemistry, is the soul of organic chemistry. So he says that Alfred Werner's contribution is just like that, the tetrahedral carbon of organic chemistry. So now we will begin with the Werner's experiment. So Alfred Werner did a lot of experiments. So he was actually the first, person to discover these types of compound. So he did an experiment where he mixes these two salts, this cobalt chloride and ammonia. So one by one he is replacing the ions. So the number of ions which gets precipitated are 3 to 1 whenever he is changing the composition. So what Werner, he conducted an experiment by mixing silver nitrate solution with this COCl3.6 NS3. All three chloride ions are converted into AgCl. So he is getting, three chlorine ions are getting precipitated. So he is getting 3 AgCl. However, when AgNO3 was mixed with COCl3, 5 NS3. Now see, it was 6 here, now it is 5. So he got 2 moles of AgCl. So in this case he got 3. So when he is decreasing the number of ammonia, so this AgCl is also decreasing. Further, when he mixes this 4 NS3, so he is getting only 1 mole of AgCl. So based on his observation that Werner was doing, so he, proposed a new theory and he gave several postulates. So we will discuss this question after this. So these were the Werner's observations. So what he observed, that many compounds are brightly colored, but again, same metal and same ligand, just because of the different composition, they are having different color, different geometry and different chemistry. So it was very interesting to him. So this was his, observation, that when he is using 6NS3, the color is orange. When 5, it is purple. With 4, it is green. With again 4NS3, but now it is, moving from cis to trans geometry. So we will discuss cis trans at the end. So when the geometry is changing from trans to cis, there is a change of color from green to violet. So these experiments were, quite interesting. Based on his observations, he proposed several postulates. So Alfred Werner in 1898, he proposed a theory for the, coordination compounds based on his observation. So the first postulate is The central atom is having two types of valencies, two types of valencies. So before this, we have, read about valency in class ninth. Valency, is the combining capacity of an element, which, we roughly take it as the number of valence electrons. When it is less than 4, it is the number of valence electron. When it is more than 4, so we calculate valency as 8 minus valence electron. So, we get that valency in the same in that way. But now Werner is saying that coordination compounds, they have two types of valency. First, primary, and the second one is secondary. So these are either, you can say, linkages or valencies. Second point, primary linkages are ionizable. Ionizable means they get dissociate when they are dissolved in water, whereas and these primary valencies are satisfied by negative ions. So these were the two important points regarding primary valency. They are ionizable and they are primarily negative ions. Third point, secondary linkages are non-ionizable. That means only primary are ionizable, whereas secondary linkages are non-ionizable. So primary linkages are negative, whereas the secondary one, these are satisfied by either negative ion or neutral molecule. So in secondary, there is a possibility of both negative or neutral. So also the secondary valency is fixed for any metal and it is equals to its coordination number. So this part is very important. So basically, secondary valencies are nothing, just the value of coordination number. Coordination number is the number of bonds uh, between ligand and the central metal. So these are the ions bounded by secondary linkages to the metal exhibit characteristics spatial arrangement corresponding to the different coordination number. That means the secondary valencies, they align themselves in a around that central metal in three-dimensional space, that they get a distinct arrangement. So we will discuss it like tetrahedral, square planar, and then we have octahedral geometry. So this is about secondary linkages. Secondary linkages. Now this is the breakthrough of whatever Werner said. So when he is varying that amount of ammonia molecule, so he is getting different observations. So based on his observation, he gave his theory. We talked about primary valency, which are ionizable, satisfied by negative ion. Secondary are non-ionizable, and they may be neutral, they may be negative. Now, the primary valencies, they correspond or they are calculated in oxidation state. They are included for the calculation of oxidation state, but the secondary valencies are, they represent the coordination number. These are non-directional, whereas the secondary valencies, they dictate the polyhedron like tetrahedral, square planar, and octahedral. So this is the difference. We have already discussed these pointers. So between primary valency and secondary valency. Now, there were several limitations of Werner's theory. The first one is it fails to explain the magnetic character, means whether the compound is paramagnetic or diamagnetic. It has no idea about where this color is coming from, and the optical properties, like we will discuss it, the dextrorotatory nature, levorotatory nature, or the chirality. So Werner's theory is unable to explain these points. Second is it also failed to explain the reason why all elements don't form coordination compound. So why only D block? Why only D block elements are there? Why not elements from S or P block are forming coordination compounds? It fails to explain the directional properties of bonds in coordination compound. Why there is a these bonds have directional properties because of the movement of electron from ligand to metal. This theory does not explain the stability of complex. So it has no say regarding which complex is more stable. So when we compare the stability, Werner's theory has no say regarding the stability. Now, this theory could not explain the nature of the complexes, means what type of complex is this, like we will discuss in valence bond theory, whether it is inner orbital, outer orbital, magnetic, paramagnetic, whatever other details. So Werner theory was, having a limitation regarding the nature of the complexes. Now, what is a coordination entity? So it is a chemical compound in which the central central ion or atom is bounded to a set of number of atoms. So means it is an entity where this metal and ligands are present. So that entity is called coordination entity. So like this is the case. Some example of coordination entities are this COCl3 and means chlorine, Cl3 and NH3. And then we have potassium ferrocyanide or ferro, this hexacyanoferrate. Then central atom, we all know central metal is the this metal ion which is present at the central. So it is central atom or central ion, which is also a Lewis acid. Lewis acid means it is a electron pair acceptor. So it is written here. So central atom is also a Lewis acid and electron pair acceptor. So this is all, right till now we have discussed. So if I take this example of K4FeCN6 potassium hexacyanoferrate, so whatever is written outside left side of this coordination sphere is called counter ion. So it is generally cation and positive, means positive entity, K plus or Na plus or anything. And then second one, the first member, inside this square bracket or coordination sphere is central metal atom. It is also a Lewis acid and electron pair acceptor. Third one is these ligands. So whatever is written after the central metal is ligand. So ligand is a Lewis base. It is electron pair donor. Now whatever number is written along with that ligand is called a coordination number. So total number of ligands. Coordination number is what? It is the total number of ligands which are, directly bonded with the central atom. And this square bracket, this large bracket is called coordination sphere. That's all. Now, what are ligands? So ligands, these are the atoms which donate electrons. So these are the atoms, molecules or ions which are bound to the coordination center of the central atom and are referred as ligand. That means which donate electron. So these ligands can either be simple. So these could be simple like we have chloride, iodide, bromide, nitrate like these, like this, or in form of relatively large molecules. So they may be bigger in size also, like we have ethylene diamine, or we have, oxalate ion, COO minus and COO minus, oxalate ion, or it could be acetyl acetonate, or it could be EDTA, like we discussed, ethylene diamine tetraacetate. So this may be simple, this may be a bigger large molecule. Now classification of ligand, very important topic, very important. So before we begin with this classification, there is a definition of denticity. So what is denticity? Denticity, it is the number of lone pairs of electron donated by the ligand to the central metal atom. Okay, so it is the number of electron pair donated. So a ligand, uh, it can donate one pair of electron, it can donate two pair of electron, it can donate three pair of electron. So if a ligand is donating one pair, it is called unidentate. If it is donating two pair of electron, it is called bidentate. Now if it is donating more than two, it is called polydentate. Okay, so we will discuss this ambidentate category. So if one electron pair uni, if it is two bi, then if it is more than two, it is poly. So like we have Cl minus, Br minus, chloride, bromide, cyanide, carbonyl. So all of these are example of unidentate ligand. Uni means one, dentate means denticity. Denticity means number of bonds a ligand can form with the central atom. Bidentate means when any ligand can donate two pair of electrons. So like we have ethylene diamine. So one pair from this side, one pair from this side. Second example, we have discussed oxalate. So oxalate is, one pair from this side, one pair from this side. So it can bind with two sides. Similarly, it can bind with two sides. So these, they are bidentate or didentate. The third category is polydentate. So if it is donating more than from more than one site, so it is called polydentate, means more than three bonds at the same time. Now, this category is very important in ligands. So, most important category is ambidentate. Ambidentate, these are the ligands in which two different atom can donate. In which two different atom can donate, but they will donate only once at a time, one at a time. But they can donate from two different sites, like the very common one is cyanide. So if the ligand is cyanide, so we will write it like this. So in this case means carbon is making this bond with the atom. But if I write this cyanide as NC, now this nitrogen is making the bond with that atom. Now the name will be isocyanide. Isocyanide. Similarly, we have this SCN. So in this case, sulfur is making the bond. So the name is thiocyanato, and with dash we write S. This S represents that sulfur is making the bond. Now, if this SCN becomes NCS, now nitrogen is making the bond. So instead of thiocyanato S, we will write thiocyanato N. That is the difference. Now, again, important ligand is NO2. So NO2 is called nitro. So when we write nitro, so we write nitro N, in which means nitrogen is making the bond. This nitro can be written as ONO. Now this oxygen is making the bond, and the name also changes. It becomes nitrito O. So we will write O. This O represents oxygen is making the bond. This N means nitrogen is making the bond. So these ligands, thiocyanato, nitro, nitrito, and the third that we discussed, cyanide and isocyanide. So these are the examples of ambidentate ligand. Ambidentate ligand. That means the same ligand can donate from two different sites, then that particular ligand is called ambidentate ligand. So these are the examples of the classification of ligand. So we have negatively charged ligand, cyanide, nitride, hydroxide, nitrate, fluoride, chloride, bromide, oxide, like this. And then we have positively charged ligand, nitrosyl, nitrosyllium, hydrazinium, like that. Then we have neutral ligands like carbonyl, carbon monoxide. Then we have ammonia and water, hydroxylamine, methylamine. So these are the example of neutral ligands. Denticity, we have already discussed. Denticity, it is the number of donor groups or number of bonds ligand can have with the central metal. So based on the denticity, ligands are classified as unidentate if one donor side, bidentate, polydentate, ambidentate. This is another category of chelate ligand. Chelate means ring formation. So this is a property especially of polydentate ligand, which can bind with more than two donor site, and when they make bond, so it forms a sort of ring like this, like we discussed in case of chlorophyll. So we have lot of ring, porphyrin, at the center we have magnesium. So wherever there is a ring formation, so that particular ligand is called chelate ligand, or the property is called chelation. So based on the denticity, ligands are classified like this. So now let us discuss it one by one. Monodentate and unidentate means which can bind only with one donor site, like chloride, bromide, iodide, cyanide, water, like this. Bidentate, which can bind with two donor sites. So like we have ethylene diamine. So it can donate from this side, also from this side. This is a case of oxalate, oxalato. So from here also and from this side also. So one molecule is making two bonds at the same time. Similarly here also one molecule is making two bonds at the same time. Polydentate, so very famous example is of EDTA, ethylene diamine tetraacetate. So you can see this CH2 means ethylene, Then we have diamine, one nitrogen, diamine, then tetraacetate. So CH2COO, one group, CH2COO, two group, three group, four group. That is why the name is ethylene, diamine, then this tetraacetate. So we write it as EDTA. Now you can also write 4 minus because one negative charge here, 2, 3, 4. So EDTA 4 minus, this is the structure. So these are the example of polydentate because it can, donate electron from this side, from this side, from this side, from this side. 4 denticity is 4. Chelate ligands. So chelate ligands are the ligands which, when they form, when they make bond with the central atom, so it makes a sort of ring. So that ring is called chelate. And these types of ligands are called chelating ligand. And the process is called chelation. So you can see these images. So in this case, COEN3 means ethylene diamine is 3 times. So this 3 time ligand means bidentate and 3 time. So it is making a sort of ring. So one ring here, one ring this side, one ring this side. Also, one interesting property is that denticity, it increases the stability. So suppose we have two compounds. The first one, a simple one, versus any compound in which chelation is there, ring formation is there. So ring formation means chelate compound will have always higher stability than the normal one. So chelation increases this stability of the particular compound or ring. So similarly, we have EDTA. So you can see this image EDTA. So this is EDTA. EDTA is making bond with this lead. So in this way, we remove this lead poisoning from that any water. So this is a case of lead removal of lead poisoning using EDTA. So in this way, this ligand, captures that particular metal and it removes that particular metal from the water. Hence, the purity of water increases. Chelate effect. So chelate effect means whenever there is a formation of ring and this ring, the formation of ring is called chelation, and chelation is, it increases means more the number of chelate rings, more is the stability of complex. This is important. More ring formation, more stability of the complex. Ambidentate ligand we have already discussed. So like we have nitro, then nitrito, cyano, isocyano, and then thiocyanato and isothiocyanato. So ligand having more than one donor sites like nitro, CN, SCN, and then we have that cyano and isocyano. So this is a complete overview of the types of ligand. So in monodentate, we have water, ammonia, fluoride, cyanide, thiocyanide, hydroxide, nitrate. These are example of monodentate. In bidentate, we have ethylene, diamine, bipyridine, then often oxalate, carbonate. These are the example of bidentate. In polydentate, we have, diethylene, triamine. So in short, we write it as diethylene, triamine. This is triphosphate ion. Then we have very famous EDTA 4 minus. So these are the list of example of ligands. Then we have coordination number. Coordination number, it is the number of bonds a central metal is having with the ligand. So like in this case, NiNH3 4. So this 4 is the coordination number. So coordination number is the 4. Like we have in K4 FeCN6. So if it is FeCN6 K4, so again this number is 6. So coordination number will be 6. So it is the number of bonds a ligand is having with the a ligand is having with the metal. Now we can calculate this coordination number. So in case of when monodentate ligands are there, so in case of monodentate, coordination number is the number of ligands, simple, like in this case in NS34 and in that hexacyanoferrate. K4FeCN6. So if the ligand is monodentate having only one denticity, so that would be the coordination number. But in case of polydentate ligand, like we have bidentate, tridentate, tetradentate, so whatever is the number of ligand multiplied by the denticity. So if I have to write the example, suppose I write this example PTEN2 2 plus. Now what is the coordination number? So if you are writing 2, so answer is incorrect. Why it is incorrect? Because this ligand is not simple. This ligand is bidentate. En means ethylene diamine. So its denticity is 2. So denticity 2 multiplied by total number of ligands. So the coordination number will be 4. So 4 is the correct answer. Okay. Similarly, if I take one more example, the CO, and I write it as, suppose I write NH3 2, and then I write EN2. Now what is the coordination number? So if you are writing it 2 plus 2, 4, again 4 is incorrect. Why 4 is incorrect? Because this is simple ligand, fine, but this is not simple. This is a bidentate. So for simple, we will take it is as it is, but this ligand is bidentate and number is 2. So 2 into bidentate is 2. So 2 2s are 4 plus 2, 6. So 6 is the correct answer. In this way, we calculate that particular coordination number, multiply by the denticity if the ligand is polydentate. Now, coordination sphere and coordination complex, coordination number, this we all have discussed. So whatever present inside this square bracket is called coordination sphere, and this particular entity, if it is written with some charge, positive or negative, so this is called coordination complex, and whatever ions are written on this side, this is called ionization sphere. Whatever written on the left side is called counter ion. This side is ionization sphere. Ionization means these are going to ionize. So anything which is written outside this bracket is of course going to be the ionization sphere. What is coordination polyhedron? Very important. So whenever ligands are forming bond with the central atom, so that particular number of secondary valencies, what that we call as coordination number. So those valencies they align themselves in such a way that repulsion between those ligands is minimum. So if total we have two types of cases in our syllabus, ML4 and ML6. That means one metal and 4 ligand, and one metal and 6 ligand. So ML4 can have two types of arrangement. So either tetrahedral or square planar. ML6 we have only one possible arrangement, which is octahedral. So these are the examples of coordination polyhedron. So it could be tetrahedral, it could be square planar if the number of ligands are 4, and it could be octahedral only when the number of ligands are 6. That's it. So these are the example of coordination polyhedron. Now, how do we calculate oxidation number? Very important, because in every nomenclature you have to write the coordination number in Roman numerals. So how do we calculate oxidation number? So the oxidation number of the central metal can be calculated by finding the charge associated with it when all electron pairs are, that means when there is a formation of coordination compound. So after the formation of coordination compound, we should know what is the charge on a particular ligand, and then only we can calculate this coordination number. So let us look at this first example. So again, what you have to do, you have to refer to this particular list, this one. So the charge is -1, -1, -1. These are the charges, -1, and this is -2 case oxide. Similarly, we have sulfate SO4 2 minus. This is also a -2 case. Then we have carbonate CO3, again -2 case. So we should know this charges on these ions. And then we have positive ligands. So positive ligands, these are not in Means we don't need to look after them because we are dealing with only this and this. So neutral molecules, they do not contribute. They have no contribution towards oxidation number. This you have to keep in mind. So if the ligand is, carbonyl or ammonia or water, so their contribution is zero because they are neutral. So now let us calculate this oxidation number. So right now I told you the contribution of ammonia is zero because it is neutral ligand. It is NCS, so charge is -1. Now we have to calculate for cobalt, so I will assume it as X. So it is written already X, and this contribution by NCS is -1 plus, we have to add this number. So 5 times ammonia, but contribution of ammonia is 0, is equals to, now when this complex is undergoing, ionization, so what will happen? Anything which is written outside this bracket is going to ionize. And what is the charge on sulfite ion? SO3 minus is 2 minus. Like sulfate, SO4 2 minus. Similarly, we have SO3 2 minus. So if the charge on this anion is 2 minus, that means this complex must be 2 plus, because these salts are always neutral. So if complex is having 2 plus charge, so we will put equals to plus 2. So when you solve this one, so this becomes x minus 1. So when this minus goes to this side, it will become plus. So 2 plus 1, 3. So the total oxidation number of this particular atom, cobalt atom, is plus 3. You can also write plus 3. Similarly, in this case, contribution by ammonia is 0. So 4 into 0, you can directly write 0. So for cobalt, I am writing it as X. 4 contribution by ammonia is 0 plus 2 times chlorine. So 2 charge on chlorine is -1 is equals to, again, SO4 is 2 minus. So this complex will have 2 plus. So is equals to plus 2. So when I write it, 4 into 0 is 0. So 2 minus 2 is -2. So this will be plus 2. So X will come out to be plus 4. So that is the oxidation number on this particular cobalt atom. Okay, so now these are the questions that you should practice. Specify the oxidation number of the metals in the following coordination entities. So find out this coordination number on this one. So again, let us assume cobalt as X plus contribution by water is 0 because it is neutral. So I'm writing it as 0 plus cyanide is contribution is -1. En2, again ethylene diamine is again contribution is 0 because it is neutral, is equals to total charge on the complex is written plus 2. So I will put it as plus 2. So X plus 0 plus 0. So X minus 1 is what? 2. So X will be plus 3. So charge on this coordinate cobalt is plus 3. Similarly, I can take another example, this one. So PtCl4 2 minus. So Pt, I am assuming Pt as platinum as X. So 4 charge on Cl is -1, and now the total charge on complex is 2 minus. So I will write it as -2. So X minus 4 is equals to minus. So X will come out to be plus 2. Okay. Then K4FeCN6, it is directly plus 3. So because Cn is -6 and this is plus 3. So -6 plus 3 is equals to 0. So this will come out to be plus 3. So you can solve these questions. Now, what are homoleptic and heteroleptic complexes? Homo, wherever this word comes, homo means same. Hetero means different. So the complexes in which only one type or same type of ligands are present is called homo, and the complexes where different types of ligands are present is called heteroleptic. So I will give you the example like this one. Sorry. So in this case, we have one ligand ammonia, another ligand chlorine. So two different types of ligands. So this will be hetero. Whereas this one, first one, so only 4 ligands and all 4 are cyanide. So this will be homo. Similarly, we have NiCO4 homo. This is also homo. This is also homo. So these are the examples of homoleptic. Homo means wherever only one type of ligand is present. Okay. So now let us talk about the properties of coordination compounds. So coordination compound, they are formed by the transition element. Transition element means D block elements. D block. And what is the characteristic of D block? They have vacant d orbital. Vacant d orbital, that means electronic transitions are possible. So because of that, they are mostly colored, like copper is blue, iron is green. So because of the vacant d orbital, they are colored due to unpaired electron and they absorb light. So like I just told you, the iron is, is green, and that iron 3 is written as brown or yellowish brown, and copper is blue. So because these d block elements, they have vacant d orbital. So when the coordination center is a metal, the corresponding coordination complexes have magnetic nature. Again, magnetic nature is because of the unpaired electron, vacant d orbital and unpaired electron. Coordination compounds, they exhibit variety of chemical reactivity. They can be part of inner sphere electron transfer reaction as well, and outer sphere electron transfers as well. So we will discuss this part in the second part of this lecture, where we talk about this valence bond theory. So complex compound with certain ligand have the ability to add in the transformation of molecule. So like I told you, the example of Ziegler-Natta catalyst. So these, because of these coordination compounds, they have d block elements. So d block elements are bigger in size, vacant d orbital, so they can accommodate more electrons. So that is why they have a good catalytic property. So they are also a good catalyst. What are the catalysts? Catalysts, they decrease that activation energy barrier and speed up the reaction rate. Now, there are various types of coordination complexes. So based on the charge, so it could be cationic complex, like we have this one. So when this ionizes, so we get 3Cl minus, and this compound will get 3 positive. Anionic complexes like this one, K4Fe6. So when it dissociates, so it will give 4K plus. So complex will have 4 minus. This side we have 4K plus. So these are example of anionic complexes. Then we have neutral, like NiCO4. Carbonyl is neutral ligand, zero contribution, charge will be 0. So we have only mononuclear complexes in our syllabus. Polynuclear is not in our syllabus. Mono means one, nuclear means nucleus. Nucleus means central atom. So coordination complexes in which only one central metal is present are called mononuclear, like we have this. So only one metal is present, but polynuclear not in our syllabus. But you should know. Polynuclear means where more than one transition element is present, like this. So we have rhenium. These two are, joining together, like this carbonyl case we discussed. So we can see this one, two metals. So when we have two metal ions, means two nucleus, so it is called polynuclear, but we have to deal with only mononuclear complexes. So again, it is just an overview of the ligands, whatever we have discussed. And now we are moving towards that nomenclature part. So how these ligands are named, how do we write their name? So if the ligand is negative, we write the, suffix O. Like for chloride, we write chlorido. For oxalate, we write oxalato. For cyanide, we write cyano. So we have to add this O at the end. And for neutral, in which there is no charge, so we write it as such. Like for water, we write as aqua, or even some books are writing as equo, but I think aqua should be the preferred one. Then for ammonia, it is neutral, we write it as amine. So only you have to remember, if the ligand is negatively charged, then we have to write that suffix O, oxalato, chlorido, like that. So this is an overview. So water is written as aqua, ammonia is written as amine, NO nitrosyl, CO carbonyl, then ethylene diamine is written as EN, it is dimethylene triamine, diene, Now, this negatively charged ligand. Now you can see this fluoride is written as chloro, bromo, hydro, hydroxo. Why? Because negative charge is there. Similarly, O2 minus is oxo, Cn minus cyano, Nc minus isocyano, thiocyanato, nitrito, ONO. So ambidentate. This one also ambidentate. ये भी ambidentate. This one also ambidentate. Now this carbonate is written as carbonato. Oxalate is written as oxalato. This SO4 2 minus is written as sulfato. So underline atom, it represents the means the bond, the atom which is making bond. So now the thing is negatively charged ligands are the name ends with O, oxo, cyano, oxalato, carbonato, etc. So that is the beginning of this nomenclature. Now the important part of this part 1 video, IUPAC nomenclature of the coordination compound. There are certain rules. Although you don't need to remember these rules, you have to directly start writing the names. But let us quickly go through these rules. So the ligand is always written before the central metal. So the name the ligand should always be written before the central metal. Rule number 1. And if more than one ligands are present, suppose we have chlorine and we have bromine and we have uh, NH3 also. These three ligands are present. Now, while writing the names of the ligand, alphabetical order has to be followed. So, like for amine, we have initial A. For bromine, we have initial B. For chlorine, we have initial C. So, name of amine should be written first, followed by bromine, then chlorine. So, it would be amine, bromo, chloro, like that. So, alphabetical order is to be followed while naming more than one ligands. Third, when there are more than one monodentate ligand, like I have written CS3, now the CS3 is 4. So instead of writing amine 4 times, we write tetraamine. So we have to use these prefixes, whatever is the number. Suppose it is twice, then we write diamine. If it is thrice, we write triamine, tetraamine, and so on. Pentamine, hexamine, heptamine, and so on. So whatever is the number, we have to write that prefix. In case of polydentate ligand, this part is important. Now, if the ligand is polydentate, suppose I have ethylene diamine, that too twice. Now I cannot write, by ethylene diamine. This is incorrect, because for to name any polydentate ligand, this prefix is not used. Bi is not used. Suppose I have to write EDTA, then it is 4. Then I cannot write tetra ethylene diamine tetraacetate. No, these prefixes are only for monodentate ligand. So when we are naming polydentate ligand, the prefixes are bis, pris. You can see this one. So prefixes are written bis, pris. Suppose I am writing EN3. So now the name will be tris ethylene diamine, whatever it is. So it should be tris. If it is EN4, so it will be tetrakis. Okay, so if it is EN2, so it will be bis. So for polydentate ligand, the prefix is different. It is not di-tri. Instead of di, we use bis. Instead of tri, we use tris. Instead of tetra, we use tetrakis, and so on. Now, that we discussed. So when we are writing the name of anions, so the end with the letter O, like chlorido, sulfato, chlorido, cyanido. Cyano also written, cyanido, both of them are correct. So you can either write cyanido, chlorido, bromido. Now when the ligand is neutral, so name is written as such, no specific name. For NH3 we write amine, for water we write aqua or aquo. Aqua should be, both of them are correct, but I would go with aqua. CO is written as carbonyl, NO is written as nitrosyl. So after the ligands are named, the name of the central metal. Now after writing ligands, we write the name of the central atom. Now if the complex is having an ionic charge, like we discussed in this case, where is that case? If the complex is negative, so this complex is positive, so there will be no change. But if the complex is negative, like I think we have discussed one case where the complex is negative. Where is that? Okay, fine. So I can write it. Fine. So I will write the example. So like I have this case K4 FeCN6. So if suppose this is the complex, so when we write the complex, so it will give 4K plus FeCN6. Now since it is 4K plus, this complex will be 4 minus. So this rule applies to this complex. So after the ligand is named, the name of the central metal is written if the complex has an ionic charge. So this complex is having an ionic charge. So the name of that particular metal is, it ends with 8. So like for this, we write the name as hexacyano for hexa for 6, cyno for this ligand because it is negative. So we have to write the name O, cyno, hexa, cyno. Now this name is, so the complexes for the metal for which we have the Latin name, we use the Latin name. So for iron, we write ferrate. Now we have to add this 8. Why? Because the complex is negative. So the name would be hexacyanoferrate. Ferrate. Why 8? Because complex is negatively charged. We will take more cases, more examples. When writing the name of the central metallic atom, in an analytic complex, priority is given to the Latin name. So that is why instead of ironate, we write ferrate. So instead of, you take any Latin name like we have for, you know, we will discuss this example like we have for copper. So we write cuprate, and so on. Okay. So exception is given for mercury. We don't write, mercury for uh, Hg. We don't write hydrogyrate. We only write mercurate. Okay. Now rules for again the continuation. So oxidation number of central atom, it must be written with the help of Roman numerals. Important. And that too enclosed in parentheses. So suppose we are writing 3, so we will write 3. For 4, we will write 4. For 1, we will write 1. But 0 is written only in this way because we have only this possibility for 0. Now, if the coordination number is accompanied by counter ion, so suppose anything written before that on the left side, so cationic entity must be written before the ionic entity. So even before writing the name of that ligand, we have to write the name of counter ion. So now let us directly get into this one. So K4 FeCN6, this is having counter ion. So name first for this counter ion. Potassium will be written first. Now when you are writing the name, you don't have to mention this number. You don't need to write, tetra potassium. No, it is incorrect. For cation, we just have to write the whatever cation is present without specifying its number. So potassium. Now, the moment you enter inside that square bracket or coordination sphere, now first you have to write the ligand. So hexa for this 6, hexa, and ligand is cyanide, so we'll write cyano because the ligand is negative. So O should be added, cyano, hexa, cyano. After this we have to write metal. So we have metal as ferrate. Why ferrate? Because this complex is having 4 minus, 4 minus because this is 4K plus. So everything has to be, you have to keep in mind. So name would be potassium hexacyanoferrate. After this, mention the coordination number. So this is 4, this is 6. So coordination number will be 2. You can calculate this also. So potassium hexacyanoferrate 2. Now for this one, second one, first name this ligand. So tetra for 4, tetra again cyano, tetra cyano, and this complex is again having negative charge. So nickel is written as nickelate. Again, you have to add the name 8. So this is 4 minus, this is 2 minus. So again, charge will be 2. So tetracyanonickelate 2. Now, see, in this case, charge is not mentioned here. What we have calculated charge on it. But in the second case, directly charge is mentioned here. So after this name, we will write ion also. Why? Because this ion is given. This is complex. Okay, negative charge. Similarly for this one. So write 4 for tetra. This OH is hydroxido. Yeah, hydroxo you can write. So tetrahydroxo. Now zinc is written as zincate because this is 2 minus. So tetrahydroxo zincate. Now the coordination number, sorry, this oxidation number will be again 2. So tetrahydroxo zincate 2. Again you will write ion because this is 2 minus. Carbonyl is a neutral ligand. This will be simple. Tetra carbonyl. Now this carbonyl is neutral, so charge is also 0. No charge, so no change in the name. So you will write tetra carbonyl nickel only. If it would have been negative, then you have to write nickelate. It is 0, so you will write tetra carbonyl nickel. Again, oxidation number is 0, no charge. So tetra carbonyl nickel 0 directly. So rest, practice these two questions. Look at these answers. Potassium hexacyanoferrate 2. So don't forget to add this ion. Why ion? Because this is ion. Similarly, the rest there is no ion. So ion is written only when the 2 minus any charge is given on the complex. Tetracarbonyl nickel 0. Then okay, this is important because this is bidentate. So En3. So En is a bidentate ligand, not a simple one. That is why we are using this name tris instead of tri. We are using tris ethane 1 2. You can also write tris ethylene diamine chromium 3 chloride. So this again it is Cl3, but we are not writing trichloride, only chloride. So anything which is written outside these these brackets, you don't need to specify their number. Just write the name. So this is just the overview, step by step, how to name any particular compound. So we have two cases, this complex 1 and this one 2. So step by step is given how we arrive at these two final names. So these are the questions for practice. So again, you can take two types of ligands are present. So for water we have aqua, for ammonia we have amine. So look at the alphabetical order. A, compare the next letter. So this is Q, this is M. So amine would come before aqua. So name would be uh, tetraamine, tetraamine, diaqua, diaqua. Then you can write the name of cobalt, cobalt. And what is the oxidation state? This is neutral, this is neutral. So contribution 0, 0. So this will be 3 minus, this complex is having 3 plus. So cobalt 3. Then outside this you can write chloride. Tetraamine, 4-amine, diaqua, cobalt 3 chloride. Now this is bidentate ligand. So name would be, now you cannot write tri, you have to write tris. Then you can write ethylene diamine, then chromium, charge is again 3 because the contribution of ethylene diamine is 0. This is 3 minus, so complex will be 3. Then again you can write chloride. So trace ethylene diamine chromium 3 chloride. Okay, so one more example that I can take is this one. Na2. So first you have to write the cation, then you will write sodium, then in bracket this is okay, so this is written CS3COO4. So this is Okay, ethylene, this ethylene diamine and tetraacetate. So this is EDTA. So you will write the name. 4 tris, sorry, tetrakis sodium tetrakis. Then you will write the name. This En for this compound, the ligand, and then chromium. Chromium. This compound is neutral, so this state will be 2 because of this sodium 2, chromium 2. So in this way you can write the name. Okay. Then again, these are the questions which you can practice. Very important ones. Okay. So okay, this you can take look at this case. Na2. So first we are writing sodium. Then F4 means tetrafluorido. Where is this? Tetrafluorido. Then O means oxo. Oxo. Both of them are negative ligand. Then we have chromate. Why chromate? Because two this will be 2 Na plus, so this charge will be 2 minus. So chromate 4. 4 is the oxidation number. Okay, fine. So these are the things that you have to keep in mind. So central atom is listed first. Then ligands are arranged in alphabetical order, and it does not this placement of ligand does not depend on its charge. Rather, you have to follow the alphabetical order. Polydentate ligands are also listed alphabetically, but that abbreviation changes from that ditri to bis tris and so on. And when you are writing these ligands, so oxidation number has to be mentioned in parenthesis. There should be no space between the ligands. So when you are writing the name of the different ligand, there should be no space between the ligand and the metal coordination sphere. So when the formula of a charged coordination entity is to be written without the counter ion, the charge is indicated outside the square bracket. Okay, so when you are writing this, a charge, so it should be written outside this coordination bracket. But if the charge is negative, then the name of the central metal must end with 8. Like for this case, it would be hexacyanocobaltate. But in this case, it is positive, so there will be no 8. It will be just chromium. Okay, fine. So this is what we have discussed one by one. So cation first, then ligand, then you have to modify the anionic name. So for anionic name, it must end with O, like chlorido, sulfato, and for neutral, there should be no change, like amine, aqua, carbonyl, nitrosyl. Then this is the important part, metal and oxidation state. So when the complex is negative or it is anion, then the name of the metal must end with 8, like cobaltate, chromate, cuprate, etc. And the name should also be written in Roman numerals. So whatever we have discussed till now, so this is the name of the metal, cobalt 3. Why 3? Because this is neutral. 0, this is also neutral. So only 3 because of this Cl3. So cobalt 3, then we have tetraamine, 4amine, then 2 aqueous, then these outside this we have only chloride. You don't need to write trichloride. Okay, then we get this name, potassium for cation, then 6 cynos, then iron written as ferrate. Why ferrate? Because when this dissociates, it will be 3K plus, and this complex will have 3 minus. So because of negative charge, the name changes from ferrous or iron to ferrate. So we get this name, potassium hexacyanoferrate. Similarly, for this, we get the name tetraamine diaqua cobalt 3 chloride. That's all about this coordination, nomenclature of coordination compounds. So again, if you find this helpful, please like, share, and subscribe. Share with your friends. In the second part, we will have only 2 parts. In the second part, we will discuss about this isomerism in coordination compounds and VBT, CFT, and so on. Thank you so much.